kind of windy today, sort of getting to be fall. I'm going to explain how I set up double integral and triple integral problems. I think that, from your point of view as a student, the difficulty of these problems is actually visualizing the 3D object and being able to kind of rotate that around in your head and imagine it. So that's really the skill that you're practicing here is visualizing three-dimensional objects and understanding how we describe those. Usually the setting up the integral part isn't so bad. The method that I use for setting up multiple integrals, I call the laser beam method. And this is the way it works. What you do is you look for a simple laser beam. What that means is you shoot a laser beam parallel to one of the axes, and what you want to have happen is only one place where the laser beam enters the object and exits the object. Okay, so then you set up an integral, where you put where it enters on the bottom and where it exits on the top, and you're setting up your integrals from inside to out. And then you just delete that axis and you just repeat the process until you run out of axes. I think I've cooked up a pretty simple example to illustrate the laser beam method. What I'm asked to do is find the area. So this means that I'm going to be doing something like the double integral of 1dA. Okay, and then here's the region. The region is only in the first quadrant, and it's bounded by the line y equals x. That's this line right here. The line x plus y equals 2. That's this line right here. And the line y equals 0. That's that line right there. And I just did a little algebra to figure out the place where all these lines intersect, and I've labeled those points. All right, so here comes the laser beam method. I only have two choices. I can either shoot a vertical laser beam or a horizontal laser beam. Let's look. In this problem, if I shoot a vertical laser beam parallel to the y-axis, then that enters at y equals 0 and it exits at y equals x. It's not going to work though because these are not simple laser beams. If I shoot this laser beam over here, then that is going to have a different set of enters and exits. Then this time, the second one there, it's going to enter at y equals 0, but then it will exit at the other line. So that's not going to work. So what I'm going to need to do is shoot a laser beam that is parallel to the x-axis. Okay, and this is going to be a simple laser beam because it doesn't matter where I shoot this laser beam. If I shoot it down here or if I shoot it up there, all the laser beams have the same enter and exit. They always enter and exit at that same, for the same functions, right? It enters here at that function and it exits at that function. Okay, so awesome. So we're using the laser beam method. The first thing that we're going to set up is the integral. Since I chose a laser beam that is parallel to the x-axis, dx is going to come first. And what this means is for this first integral, y is constant. So I have picked a single value of y, and what I want to know is what are the values of x where this laser beam enters and exits. So the first, it's going to enter at x is equal to y, and then it's going to exit right here. And what's that value? That is going to be x is equal to 2 minus y. You can see I've just solved the equation for where it exits for x because we chose dx first because that's the only simple laser beam. Okay, that's it. So we've done the first part of the step. The rest of the process is just repeating that step. It's a little bit trivial this time. So what happens, now I'm going to delete the x-axis and all I'm left with is the y-axis. So let's just look and see what would happen if you just delete the x-axis. So that just means, just smashing everything down onto the y-axis. This whole thing would get smashed down right there. So all I have left is this region right there. Basically, we're just asking ourselves for which values of y do I actually get these laser beams to go inside the region. So that's just going to be these. It goes up to this y equals 1 right there. So there is 1 there and there is 0 down there. All right, so that's it. So now the second integral we're going to do here is going to go from y equals 0 up to y equals 1 dy. And that's it. We've done it. We have used the laser beam to set up this integral. Let's look at some more complicated examples. Here's another one, flying at you pretty fast. We're now asked to find the volume of a tetrahedron, and it's bounded by the coordinates planes. It's in the first octant. This is always a bit funny. I've never seen any of the other octants named, but they do talk about the first octant. Anyways, that's just the one where x and y and z are all bigger than 0. So if you ever see that first octant, they mean the one where all the variables are positive. So we want it to be in the first octant. We want it to be bounded above by this plane. So I've graphed our little tetrahedron. I just want to show you how I did that. So basically what I did is I just found these corners right there, and I did that just by, this place where it intercepts the z-axis there, intersects the z-axis, has x and y equal to 0. So you can just plug x and y equals 0 and you get z equals 12. I think you can see I also did that here. You plug in x and z are 0 and it's going to give you y equals 6. So that's how I graphed this region. All right, let's use the laser beam method to set this up. So they're all simple laser beams. It doesn't matter which one we choose because they're all, this is such a simple shape. It all enters and exits at the same place. If it doesn't matter which one you do, I will often just choose the default order is DZ first. So let's just imagine that laser beam right there goes up parallel to the Z axis. So I'm going to do the volume. You find the volume by doing the triple integral of 1. Okay, so my first laser beam goes up parallel to the z-axis, and it enters at z equals 0, and it exits at the plane. So if I just solve this equation for the plane for z, I'm going to get 12 minus 3x minus 2y. Okay. All right, so laser beam method step 1 done, and this is dz because my laser beam goes parallel to the z-axis. Okay, now that you're done with the z-axis, now what you need to do is draw the region with the z-axis deleted. So you just smash the whole tetrahedron down into the xy plane. So now that I've reduced this to a 2D problem, I'm going to have a line. Where does it go out? It goes out on x to 4, and it goes out on y to 6. So that's going to be this line right here. And this line happens, you can see that this triangle right there, that's the same as that triangle right there. Okay, so that happens when z is equal to 0. So the equation of this line is just 3x plus 2y equals 12. Okay, so it doesn't matter. This is simple no matter which way you do it. So I'm going to go ahead and choose to shoot a vertical laser beam this time. And this is going to enter at y is equal to 0. And then if I solve this for y, it's going to exit at y is equal to negative 3/2 x plus 6. Okay, so all I did was I just solved the equation of that line for y. All right, and then since the second laser beam that I chose was in the y direction, then dy comes next. Let me just move this over a little bit. All right, okay, so we're almost done. So now I can delete the y-axis, and all I'm left with here for the last step is the x-axis. So that's just going to be like this piece right here. So from there over to there, if everything got smashed down this way, so that's just going to go from 0 to 4 here. So this is going to be x equals 0 out to x equals 4. You can see you can get that if you plug in y equals 0 right there, then that'll give you that piece right there. You're going to get x equals 4. And the last one there is dx. Okay, so that's it. We set up this integral in this order. It's kind of fun, honestly. I enjoy it. Let's see if we can come up with a problem that has only one way where you can do it correctly. Okay, I think this is a good one. I'm not I'm not wholly convinced that there is only one way to set this up, but it is a good problem. So let's have a look at this one. Again, we're looking at a solid that is in the first octant. Okay, so it's bounded by these coordinate planes, and then it's bounded by this plane, y plus z equals 1, and this cylinder, y squared plus x is equal to 2. Okay. All right, so here's the cylinder that we're talking about. It's just this sort of piece of that's a parabola. If you look at it this way, it's a parabola, and then it's independent of z, so it just goes up that same shape forever. And then this is the plane. So we're taking that kind of like sort of wedge-shaped region right there, and we're chopping it off at the top. And so let me try to draw this. Okay, so I've started to draw this solid. So I started to draw this parabolic cylinder here. So it's a parabola, but it just goes up and down everywhere in the z direction. So, you know, if I were to include everything, it would go up like this. Okay, just up forever. But it doesn't, because it's had its top chopped off by this plane y plus z equals 1. So that's going to kind of cut down right here. You know, so you're imagining that kind of cylinder, and then it sort of had, you know, samurai sword style, had the top of it sliced off. So that's going to make a kind of shape like this. Okay, pretty good. Let me try again. All right. Okay, so we get this kind of like awkward wedge shape. And what I want to explain is, in this case, so this is x and this is y and this is z. So in this case, dy is a bad choice. Let me show you. Dy is a bad choice. If you shoot this laser beam right here, then it's going to enter at that plane and then exit at the wall of the cylinder. But if you shoot this laser beam over here, it's going to enter at the plane and it's going to exit at that other plane, that slanted plane. So what I'm explaining is, when I look at this, you know, and I try to visualize it and ask myself which laser beams would work, I think that dy is not simple. Okay, I thought about it for a second, and I think that either of the other choices is going to work. So you could do dx. Let's look at these laser beams right here. So if you start shooting a laser beam up from the floor, then it's going to enter at the floor there and then exit at that plane. Since the walls of that cylinder go straight up and down, actually it doesn't matter. Any of these laser beams that you shoot in the z direction, they're all going to enter at z equals 0 and all exit at this plane right there. So I think that dz does produce simple laser beams. Also, if you shot a laser beam down this direction, then I think you are going to be fine, right? This way, you're going to enter at that wall back there. Since that top of the plane is kind of slanted down in this way, it doesn't matter where you enter it. You're always going to stay under this ceiling right there. You see what I mean? So because of that, you're always going to enter at the back side there where x is equal to 0, and then you'll always exit out that wall right there. So I think that that dx is also simple in this picture. Personally, you know, I would choose. You know, it doesn't matter, but I would choose dz for this one, just because that's kind of like my default. You know, if it doesn't matter which way you do it, choose dz first. Okay, so let's do that. So the volume here is going to be some kind of triple integral of 1, and then we decided to do dz first. So that's going to be this laser beam right here. So that's going to enter at z equals 0, and it's going to exit at this plane. So that will be z equals 1 minus y. All right, next, okay, so that's it. Now that we've done that, I can smash the whole thing down, and now I will just have a region. Since I've deleted z, I will now have a region in the xy plane. Okay, so in the xy plane, you know, if you smash the whole thing down, you're just going to get this parabola right here. Okay, and now So now we just repeat this process for this one. I actually think it doesn't matter here. If I do a parallel to the x-axis, then I will enter here at 0 and exit at this parabola. When I look at the function and I imagine either solving it for x or for y, I don't think it really matters, but you can see that if I solve this for like 2 minus y squared, remember at the end of this, you're going to have to calculate antiderivatives. The other choice would be y is equal to the square root of 2 minus x. I would rather do the first one. So because of that, I'm going to choose X next. Sometimes if it doesn't matter the choice that you make, you want to, you're setting this up so that you can do the antiderivative. So, so try to do it in a way that's simple. Okay, so for dx, this is going to enter at x equals 0, and it's going to exit right there at that line. So that is where x is equal to 2 minus y squared. And then the last one here. Okay, so now technically we have just a 1D picture because now that you delete the x-axis, you're going to smash everything this way, and all you're going to be left with is these y values right there. So what is this range for y's that I've just shaded there in red? That's going to be from y is equal to 0 up to that top point right there where, so if x is equal to 0, I guess I will get y is equal to the square root of 2. Okay, so observe that when you do this process, if you do dz first, then you should have no z's left in that middle term. Then since I did dx, this right here should have no z and no x. Okay, so if you're setting these up and you have deleted one of these axes, and then you still have that letter as one of your limits of integration, you've done it wrong. So that's just a good check. When you delete these axes, go back in and make sure that that really does get rid of all of those letters. Okay, so there's a brief introduction to the laser beam method. Probably the next thing for you to do is to get in there and try some of these homework problems, and see if you can get stuck and then maybe unstick yourself. And please let me know if you come across a problem that's tough to visualize or you just need a hint or something.